Hello everyone. In this video, we're going to be talking about forecasting error analysis. So let's say that you have data as we have here. This is the gasoline data that we used in class, and we've used multiple methods to forecast it. The question is, which of these methods should we pick if you want to keep forecasting using a single method? And you have to pick a method because at the end of the day, you need a single number as your forecast, so you can use that to do whatever planning you need to do for the next week or the month or the quarter or whatever your time horizon is. So the question we'll be answering in this video is, let's say that for this data, this is gasoline sales data in thousands of gallons. So I have a forecast of 18.5 or 18,500 gallons for the next week using the 2 period moving average. And I have a forecast for 19.39 or 19,391 gallons using exponential smoothing. Question is, which of these methods should I trust, right? So which of these forecasts should I pick? Which is a better method? Now, obviously, which method is better comes down to the errors. So you look at the errors here, you look at the errors here. Some are positive, some are negative, some are large. There are some large errors here also. The question is, which is better? If you remember correctly, for the same gasoline sales data, we also implemented the forecast including trend method. So again, we have three different methods that we've used to forecast this data, and the question that we have to answer is, which is the best method? So to do this, what we are going to do is we are going to, oh, this is something else. What we're going to do is we are going to aggregate errors. So we're going to calculate metrics called error aggregates. Error aggregate. So what error aggregates do is, instead of having one value of error for every time period that we're considering, we are going to have a single value of error for this whole method. So I'll say that the average error, some sort of averaged error for the 2 period moving average, is a number X, and some sort of averaged error for exponential smoothing with alpha is a number Y. And we'll compare the two numbers. Whichever method has the lower average error is the method that we'll end up picking, right? So lower error is always better. So that's essentially how this is going to happen now. But there are many different ways of aggregating error, and we are going to look at three major methods of error aggregation. Now the textbook has a lot more than three, but these are the three main methods of error aggregation, and those are the only things that I'm going to be talking about. Now there are other things like tracking signals and whatnot, but we'll look at that later, right? So maybe I'll do tracking signals, but not more than that. But let's calculate the error. So let's look at the error aggregates first. So there are three major error aggregates that we talk about. One is the first one is called MAD. This is mean absolute deviation. So deviation is just another name for error. The second method is called the MESSI method. So MESSI is mean squared error. And the third one is the MAPE, MAPE, which is the mean absolute percentage error. Right? So mean absolute deviation or mean absolute error, mean squared error, and mean absolute percentage error. So these are the three main error aggregates that we can calculate for our for any forecasting method that you implement. So the names essentially suggest what we are doing. The first one is the mean absolute deviation or the mean absolute error. So you calculate the mean of the absolute values of the errors. So it's basically, you just go in the reverse order, and that's what you're doing. First we calculate the error, find the absolute value of error, and find the average value of all of that. Mean squared error is you square the error, you find the average value of the squared error, and that's that. And mean absolute percentage error is you first find the absolute percentage error, then you find the average of the absolute percentage error. So let's go through one example to see how this works. So I'm going to say, I'm going to create a new sheet. Let's do error analysis here. Let me just forecast including trend. Then we will do error analysis. So for that, let me get this data first. Okay. So let me do all the borders, and rather not have any borders, frankly. So that's what we have here. So with this, so let's first calculate the mean absolute deviation, or the MAD. Now, when calculating these errors, there are two ways of calculating errors. The first one is to calculate one value of error at the end of everything. And the other way to do it is to keep a running total that you can calculate. Now, the nice thing about keeping a running total is that the running total can get updated as you add more data and you add more values of error. Let me show you both methods. First thing that you need to do is calculate the absolute value of error. So absolute value of error essentially means you want the values of, you want the same errors but without the signs. So no apps, just basically saying signs don't matter. I'm going to say absolute value of error. So it's the absolute value. So as you can see, that's the formula there. It's the absolute value of whatever error that we have. If it's 0, it's going to be 0. If it's positive, it's going to stay positive. But if it is negative, it's going to turn positive. Absolute value, it's just without no signs. Now, to calculate the MAD, you can always say, I'm going to calculate the average value. So it's the average mean. It's the average of all the error values, and that's the MAD. So that's the MAD for all the error data that you have. But the problem with calculating MAD this way is that, let's say that you keep doing this forecasting and you keep adding more and more data, then every time you have to go back and do the calculation all over again, right? Now, another way to do this is to keep a running total of MAD. So you can have a whole column for MAD, or the mean absolute deviation, mean absolute error, and you can keep a running total. So what do I mean by a running total? Running total is, first we can say, oops, I'm sorry about that. Okay, so we keep a running total. So first, the first value of mean absolute error will be the same. So, but I'm going to write this as a running total. So I'm going to say average. So what do I mean by running total? So let's do a couple of these numbers by hand, and then we'll write a formula for it. So for the first, at the first time period when we have an error, so our weekly sales were 19,000 gallons. We forecasted 19,000 gallons. So essentially there was no forecasting error, because this is calculated as the average of the last 2 weeks and we calculated it perfectly. So no error. So the mean absolute deviation is also 0. But the week after, we forecasted 20,000 gallons of liquid, but our actual sales were 23,000. Our actual demand, I shouldn't say sales, this is more demand. Our actual demand was 23,000. So if it is more, we usually just will assume that we just get it from somewhere else on a short-term basis. We're not looking at cost values, we're just looking at sales. So 23,000 was the actual sales. So our error was 3,000 gallons and our absolute error was 3,000 gallons. So how do I find so the average value should be 3 plus 0. At the end of this week, the mean absolute deviation is the average of these two numbers. The third week, it is the average of these three numbers. Week 4, it is the average of these these four numbers. So as data keeps getting added, you have to add an extra data point and average out all the data that you have. So you can keep a running total by writing the formula this way. So we'll say average of, so you still have to calculate the absolute error value, but you can keep a running total by saying average of, you always start here. So I'm going to make that an absolute reference, but the ending point will change. So the ending point will be E5 for right now, because we only have a single data point right now, so that is going to be 0. But when I copy this formula down, you'll notice that it became 1.5. Why? Because it is 3 plus 0 divided by 2. That's 3 divided by 2, that's 1.5. That's the average of the first two absolute error values. Now, how did I get that? So if you look at the formula now, so the formula will always begin at the first cell. It will always begin at E5. but the place where it ends keeps getting changed based upon how many weeks you're calculating the average error for. So this is a simple way of keeping running totals by fixing the top value and then just letting the bottom value change, right? So you fix the top value where the formula begins, but the value where the formula end changes. So this way, it's a simple way of keeping running totals. And there you go. So for the last one, if you did everything correctly, the mean absolute deviation here should be 2.7, just like we have there. And that's exactly what you have. I don't want more than 2 decimal places, so I'm gonna do that. All right, so 2.7 is our mean absolute deviation. That's better. So this is how you keep a running total of mean absolute deviation. And running total of mean absolute deviation is actually useful when I talk about tracking signals later on, but that is how you do it. And we can do the same thing with the other types of error aggregates also. So I calculated the mean absolute deviation as 2.7, right? Now let's calculate the other error aggregate. So that's the mean absolute deviation. Now let's look at the mean squared error. So to calculate that, we have to first calculate error squares. So you're going to square the errors. So nothing here, nothing here. This is going to be, you take the error value that you have, or even absolute value, because I mean, once you're squaring, it really doesn't matter whether you're doing 3 squared or minus 3 squared, right? So error squared, so square the error values. So you square the error values, and then you can calculate the mean squared error as the average of all the squared errors. Now, you don't have to take a square root or anything like that. Mean squared error is just the mean of the squared errors. Now, this will obviously be a much larger number than the mean absolute deviation. The actual value of mean absolute deviation or mean squared error really don't mean much. So is 2.7 good or is 2.7 bad? That depends upon whether your forecast values are small numbers or large numbers. If your forecast values were in thousands and your absolute errors is only 2.7 or 3.7, that is a really, really good forecast that you have. But if your forecast is in the tens and 20s and your absolute error is 2.7, that's a slightly higher error than average that you're saying, right? Okay. So all you do with these numbers, the mean absolute deviation, mean squared error, and we'll see how to calculate mean absolute percentage error. All you do with these numbers is compare them. So I calculated the mean absolute deviation for the 2-period moving average because these errors are based on the 2-period moving average. I'm going to go back. We're going to look at alpha is equal to 0.2. We're going to look at for exponential smoothing with alpha is equal to 2.2 and do a similar analysis. And then compare the MAD value of this with the MAD value of that and see whichever gives you the lower value. And that's the method that we'll choose. So that's the mean squared error. And finally, so you can also calculate a mean squared error. You can also keep a running total of the mean squared error. So if I can do average of this ending at the same point, but then I average it out, so it'll end up in the same place. So yeah, 11.25. So that's our mean squared error. So that's what you get. So you can either keep a running total or you can just calculate the mean squared error at the end. Finally, we have the mean absolute percentage error. So to calculate the mean absolute percentage error, we first need the absolute error, then we need the absolute percentage error. Now, here, this is obviously not the formula for that. So how do you calculate the absolute percentage error? So the absolute percentage error is pretty straightforward. The way you calculate the absolute percentage error is you take the absolute error value. So you have to first calculate absolute error. You take the absolute error value and then you divide by the actual sales data. So with percentage error, you're saying well, what percent of my actual sales do my error is my error? So that's the question that you're answering there. So that's the absolute percentage error. In this case, it will be 0, but I'm gonna put that as percentage. Show 2 decimals. In this case, there'll be everything is 0, so nothing will show up here. But I can calculate this at the same formula all the way down. These are all my absolute percentage values. So our error can be anywhere. So it can be either 0% or can be as high as 40%, as we had in week 11, absolute percentage error, right? So with that, we can calculate the mean absolute percentage error, which is the average value of all of these errors, which is 14.69. So that's on an average, you have an error of about 15%. That's how much error you can expect on average, right? And similarly, you can calculate a running total for the MAPE also. Same thing that we did before. We say average, start at this number, fix the top portion, end at the same point, and then copy the formulas down. And there you go, 14.69% error. That's pretty much it, right? So that's the mean absolute percentage error. So now that we have calculated this for the 2-period moving average, let's calculate this for other data, right? So let's do it for exponential smoothing with alpha is equal to 0.2. So what I will do is copy this and paste it over there. Calculate this for okay. Now we know that for exponential smoothing, so this is exponential smoothing with alpha is equal to 0.2 and initial forecast of 20. So initial forecast has to be given. So initial forecast is 20. So once you have the initial forecast, we calculate error as the actual value minus the forecasted value. And then we can go through the process. So we say that this is the previous forecast plus alpha times, so it's 0.2 times the error, right? There you go. And the error remains the same. I can carry all of this down, but I want only 2 decimal places. So I'm gonna do that. Oops. There you go. Right, so these are my forecast values and these are my error values, right? And similar to what I did before, I can calculate my absolute error values, mean absolute deviation, error, squared error values, mean squared error, absolute percentage error, and MAPE. So let's go through that process quickly, and then I'll end the video here once we do the comparison. So absolute error is the same, so just say absolute value of error. There you go, the absolute value of error, right? So once you have that, you can calculate MAD, which is the average. Actually, let me, there you go. This is the average of all my absolute error values, and that'll be 2.36, right? So my MAD here is 2.36. This method has an MAD of 2.7, so this is a better method than that. So when you're comparing two of these methods, the first thing that you need to do is pick which error aggregate you're going to look at. Not all error aggregates might not give you the same answer. You might calculate, say, for say MAPE, and end up with the idea that this is a better method than the exponential smoothing, and that's okay. You have to decide which error aggregate you trust, and you have to pick that error aggregate and do evaluate all the different methods using that error aggregate. Okay, so we can do a running total. Okay, 2.36. So then let's also square the errors. Errors squared. So the messy is the average. How come I always misspell average? Average of all of these numbers. Let me reduce the decimal places. How do I? Okay. 7.3, right? So that's the average value. 7.3, as you know. That's much lower. So if you're looking at mean squared errors, there's a much bigger difference between that two. But also remember, these are squared values, so there's always that. And of course, mean absolute percentage error, you take the absolute error divided by the actual sales. I'm gonna do all of that, change them into percentages with 2 decimal places. So you can calculate MAPE as the average value here. It's also percentage with 2 decimal places. So 12.28% as opposed to 14.69%. So again, so both MAD, MESI, and MAPE, all three of them are definitely saying that alpha of 0.2 is definitely a better method than 2-period moving average, right? So you can always calculate the average as a running total. There you go. And that's the idea. So once you have these two, you can compare the two values together. So it's already a 20-minute video, but there's one last thing that I want to talk about, and then we'll go from there. So when you have two methods, or you have more than two methods, you pick one error aggregate like a MAD, a MESI, or a MAPE, and then you calculate those values across all the methods, and whichever method gives you the lowest value is the one that you pick. But let's say that you already picked a method. Now the question is the method the right method to keep going on in the future, or should we reevaluate our method? At some point, you need to reevaluate. So reevaluating the existing method. How do you reevaluate an existing method and say that, hey, time has come for us to maybe look for another method, or maybe change the value of alpha, or change the time window that we're using, or something like that? How do you reevaluate a method? So in this case, let's say that this is the method that we picked. So I'm going to copy all of these numbers here just up to the MAD. We're not going to need the MESI for this. How do you reevaluate an existing method, right? So the way you reevaluate an existing method is to calculate something called the tracking signal. So you can calculate something called the tracking signal. Should we re-evaluate the existing method? To do that, you calculate the tracking signal, right? So what is the tracking signal? So tracking signal is a number that should be between -3 and 3. So if the number becomes less than -3 or more than +3, then it is time for you to reevaluate the method, right? Now this +3 -3 obviously is arbitrary, but it comes from the same idea as 6 sigma and also the 3 standard deviations away from the mean that you have with the normal distribution. Ideas are very similar. So how exactly do you calculate the tracking signal? So to calculate the tracking signal, first we have to calculate the MAD, but then we also have to calculate the total error. Oops. It calculates the total error. So this is something that we have to calculate. So total error is just a running total of the error, including the sign. It is sum all the errors starting from this point. So it's a running total. So I'm going to use the usual running total idea. So you start at the number and end at the same number, but the first one is an absolute value. So you're plugging the beginning of your formula here, but your ending formula will change. So you're adding up your total errors, all the error up to this point, right? So once you calculate total error and you calculate MAD, calculate tracking signal as total error divided by MAD. Okay. So you calculate the total error, you calculate MAD, and you calculate total error divided by MAD. So what you tracking signal? It's total error divided by the MAD. So this is the reason why you have to keep a running total of the MAD values and a running total of the total error values so you can calculate this. Now, you'll notice that these are numbers, so some of these numbers are positive, many of these numbers are negative. That's okay because it seems like you have a negative trend towards your error. But even the negative errors are not as bad as you think they are. So because this tracking signal is between +3 and -3, you don't have to reevaluate this method. But you can keep calculating this tracking signal over and over again. So like the name suggests, it's a signal that tells you that your forecasting method is out of whack, that your forecasting method is not working anymore. So once this signal either reaches a +3 or a -3, your bias has grown too much. And so it's time for you to stop, gather some data, uh, um, look at multiple forecasting methods and come up with a new forecasting method. So that's what you do. So that's why you calculate a tracking signal, right? So when looking at error analysis of forecasting, you have to understand the idea what the error aggregates are and the ideas behind the error aggregates. You basically calculate the error aggregates to compare across different methods that you have and use the error aggregates to pick the method. And finally, you calculate the tracking signal to make sure that your existing method is working. So if your tracking signal is out of whack, that is it's less than -3 or is more than +3, then you have to stop and reevaluate your method all over again. And this doesn't happen very often. As you see with the data that we have, our tracking signal is saying that we are still on track and we can keep using the exponential smoothing method with alpha is equal to 0.2 as our forecasting method for the future. So as we keep going, as the negative biases, maybe they add up and slowly they become large enough that you have to reevaluate the method. You don't know. So that only happens, as you can see, you're calculating a total value for error. So if some of your errors are positive, some of them are negative, then they will cancel out. And so your total error never becomes more than 6.31. So that's the worst case scenario that you had there, right? So, and that's okay. Then this is the average error that you have. So if your total error divided by the average error is within this range, you're fine. But if there is a bias, that is you are consistently under forecasting or consistently over forecasting, and that becomes large enough, then the total error becomes a large number, but the average error won't, and so the ratio becomes either less than -3 or more than +3, and then you can reevaluate your forecasting method. All right. So it's almost 30 minutes, so I think it's perfect time to stop this video. And yeah, I'll see you all next week. All right, take care.